Okay, let's go ahead and get started. Administrative business first. I have graded problem set 9 for you to pick up with solutions. Also graded problem set 8 and solutions for those who didn't get them last time. Probably what I'll do, I also have a pile of unpicked up problem sets from earlier in the semester. You might want to get those before to help you study for the exam. So maybe what I'll do is I'll put them in a box outside my office so that you can come by and pick them up at some other time. So at this point, you should have all your problem sets 1 through 9 and solutions picked up and graded. And I'll find a way of getting problem set 10 graded and back to you in advance of the midterm, of the final exam. I'll probably just leave it out for you to pick up in front of my office. Good. Okay, so I'd like to continue with our discussion of the theory of quantum mechanics. So the main lesson that we learned last class is that in quantum mechanics, the state of a physical system is represented by a wave function that will depend on position and time, and observables, that is to say, quantities that we would be interested in predicting using our theory of quantum mechanics, are represented by operators that act on these wave functions. So, for example, the classical observable x, which would tell you the position of a particle, is represented by an operator x hat. And what does that operator x hat do when you act on a wave function? Well, the operator x hat times psi of x and t is equal to a new wave function, that is to say, a new function of x and t. That's x times psi of x and t. And likewise, the momentum of an object is, in classical mechanics, just a number, but in quantum mechanics is an operator that we sometimes denote p hat. And the operator p hat acts on wave functions so that p hat acting on psi is minus I h bar times d psi by dx. Okay. So it's impossible really to overstate how different this is from our picture of observables in classical mechanics. In classical mechanics, observables are just numbers associated with the state of a system. You know, if you have a particle that's moving in a particular way, then it just has a particular value of position and momentum as a function of time. In quantum mechanics, however, the rules of the game are slightly different, and instead we associate these observables, the quantities that we would like to compute, with operators. And in order to understand what the value of the observable is in a given quantum state, we must compute expectation values. Okay. So the expectation value of some observable, let's call it A. I'll put a hat on it to remind ourselves that it's an operator, is the average value of this operator A, or of this observable A, if you were to perform many, many repeated measurements of this observable in the same quantum state. And it's given by an integral dx from minus infinity to infinity of psi star times the operator A acting on psi. So for example, the expectation value of x, the average value of x that one would compute if I gave each person in this class the same wave function and asked you to measure the position of the particle, I could average that And the result would be the integral dx of the absolute value of psi squared times x. Or more generally, the expectation value would be the integral dx of psi star times a acting on psi. And last time we saw that with this definition and with the definition of the momentum operator that I defined for you a few minutes ago, indeed, the expectation value of p and the expectation value of x are related by the usual formula that we expect from classical physics, that momentum is mass times velocity. So p is mass times dx by dt. So that, for example, if you wanted to compute the expectation value of not p, but some function of p, say p squared or p cubed or p to the 12th or something like that, then what you would do is you integrate dx of psi star times that function of the differential operator times psi. Okay. Now, usually you're used to thinking of functions of variables, not functions of operators. But if you think of everything in terms of a Taylor expansion, then it should be clear what I mean by the function of an operator. So for example, if f of p is p squared, then we'd be talking about the second derivative, the square of the differential operator d by dx. If f is p cubed, I would be talking about the cube of that differential operator, and so on and so forth. And one of the things that is important to emphasize, which I didn't quite get a chance to say last class, is that some states have definite values of certain observables. So, in particular, given an observable A, we would say that an eigenstate of the operator A hat with eigenvalue little a, which would be some number, is a wave function, that is to say, a state psi that depends on x and t, which has the property that the differential operator, or the operator A acting on psi, is just the number little a acting on psi. So that's just a definition of what I mean by an eigenstate and an eigenvalue. I assume that you guys have all seen this concept in your linear algebra classes. Is that correct? Have you all seen? Raise your hand if you've seen the notion of an eigenstate and an eigenvalue. Most people, but I see some hesitation. Okay. Raise your hand if you have not seen this. Okay. Much more definite much more definite hand raising there. Okay. So this then is just the definition of what I mean by an eigenstate and an eigenvalue. The reason why you might see this in your linear algebra class is that it's a concept that appears very frequently when we're dealing with matrices. So for matrices, let's say that we have a matrix M, which is some n by n matrix. An eigenstate, or an eigenvector of the matrix M is some vector, v, which we regard as an n-component column vector, with the property that the matrix multiplied by v, that's another vector, is equal to just some number times v, where lambda is referred to as the eigenvalue. And if you want to think about a matrix as some sort of linear operator that acts on vectors, then those vectors which have the property that the matrix acting on it is a constant times the vector will have some very special role to play. So this is not a class on linear algebra, and so I'm not going to talk about that in too much more detail. But I just want to introduce this because I want you to think about states and operators in quantum mechanics the same way that you think about vectors and matrices in linear algebra. Okay. So just so far in our discussions of quantum mechanics, we've described the state of a system as a wave function psi, and we've thought about observables as, for example, differential operators that act on that wave function to give you another wave function. Equally well, if you wanted something simpler to think about in your mind, you could think about a state as a vector, and you could think about the operators as a matrix that act on this vector just by multiplying the matrix times the vector using the usual rules of matrix multiplication. Indeed, very early on in the history of quantum mechanics, the theory had a different name. It was called matrix mechanics. Okay? Because there's a sense in which you can view the differential operator d by dx as an infinite by infinite matrix multiplying a wave function which is regarded as an infinite column vector.
Is that a matrix over the reals? I mean, are the elements of that matrix real numbers? Or are they...
Okay, so the elements of the matrix are not real numbers, they're complex numbers. It's sort of an infinite, if you want to think about it this way, it's an infinite dimensional vector space. That is to say, it is a column vector with an infinite number of entries. And usually you would label the entries in a column vector by an index, say I, that ran from 1 to 3, if you wanted to describe vectors in three-dimensional space. If you want to think about the wave function psi as a vector, you need to think about x, that continuous label there, as a continuous index. Okay. So you would think about a wave function psi not just as a column vector with an infinite number of entries, but one with a continuously infinite number of entries. Okay. And you could then think about the differential operator d by dx as an infinite by infinite matrix acting on that infinite dimensional column vector. So if you're bored in this class, then I encourage you to work out the entries of that infinite by infinite matrix. Okay. Doing infinite by infinite matrix multiplication can take all day. Okay. So, but actually it's quite easy. It's actually really not. If you remember what the definition of a derivative is, you should be able to figure it out. Okay, so why are eigenstates and eigenvalues interesting from the point of view of quantum mechanics? So if our wave function psi is an eigenstate of the differential operator A with eigenvalue little a, then if you were to calculate the expectation value of some function of the observable, so that's the integral dx of psi star times the function of the operator times psi, well, you could imagine taking that function of the operator A and writing it in a Taylor expansion as 1 plus something times A, operator A plus something else times operator A squared, and so on and so forth. And each time that operator A or A squared or one of the other powers of the operator acted on this wave function psi by acting on it from the left, you would just get a power of that number little a. So this would be the integral dx of psi star times f of a psi, okay, which if you think about it, is just exactly the value of f, so f of a, which is f of the expectation value of a. And that's because if psi is an eigenvalue of a, then then the expectation value of the operator a is just little a times the integral dx of psi star psi. And of course, the integral dx of psi squared is equal to 1. Okay, so that's just little a. So in other words, if psi is an eigenstate of the operator a with some particular eigenvalue, then the variance of the observable a is 0. So in particular, the variance, which is the expectation value of a squared minus the square of the expectation value, is equal to 0 in this state. So if you want to say this a little bit more simply, you would say that a wave function, which is an eigenstate of the operator a, has a definite value of that observable. So to state that slightly differently, every time you measure the observable a hat, you would obtain the exact same result. So, of course, not every state is going to be an eigenstate of a given observable. So not every state is going to have the property that it has a definite value of some observable. But so far in this class, we've already encountered examples of eigenstates for some observables. So just in order to make this discussion a little bit more explicit and to give you some hands-on examples to think about, let's consider the following. So let's consider the wave function psi, which is a plane wave, e to the I px minus et divided by h bar. So that's a function of x and t, where p and e are just numbers. So this is a plane wave. Then you could act on this with the operator p hat. So what is that? That's minus I h bar times d by dx of psi. And what does that d by dx do? Well, it pulls down a factor of ip over h bar, which cancels the minus ih bar out front, so that this is just the number p times psi. Okay. So that means that this plane wave is an eigenstate of p hat with eigenvalue p. So a plane wave is an example of a state with definite value of the momentum. So if I handed each one of you if I took 100 students and I handed each one a copy of the same plane wave state and I said measure the momentum of this particle, you would each get exactly the same result. The variance of the probability distribution in momenta that you would measure would be equal to 0. I should make a comment here, which is that I'm using a notation which is the sort of standard notation that one uses in quantum mechanics, where we're a little sloppy about distinguishing between observables as operators and their eigenvalues. So for example, I'm calling p hat here the operator, which is I h bar d by dx. And I'm calling b here just some number, 2, 3, 4, or something like that. And I'm using the same symbol to denote them, just one has a hat on them and one doesn't have a hat on it. In fact, if you actually read quantum books, they'll sometimes leave the hats off so that they'll use the same symbol here to denote that symbol there. And then life gets very confusing, okay? I'm going to try in this lecture to be very careful. We use hats on my operators and no hats to denote numbers. But I promise you that I'll make a mistake at some point and leave a hat off something that should have a hat. So it's just important to keep your head screwed on correctly when making sense of formulas like this. Question?
How does that not violate the uncertainty principle?
That's the thing I'm going to discuss next. Other questions? Yes?
The eigenstates, are they always stable, or is it?
No. Okay. Yeah. So let me answer both of those questions. That sort of gets to where we're going to be going next. Okay. So in the example that we're considering here of a plane wave, so if you consider a free particle, one that is not subject to any external forces, the Hamiltonian, which is the operator corresponding to the energy of the system, has the plane wave e to the I px minus et over h bar as an eigenstate with eigenvalue that's equal to the energy of the state, where E is equal to 1 over 2m p squared. So here I'm not using h, I'm using h hat to denote the operator, that's the Hamiltonian operator, or the energy operator. And I'm using E to denote its eigenvalue, which is a number, which is p squared over 2m. And so if we wanted to understand how this plane wave evolves in time, we would use Schrodinger's equation, which says that I h bar d by dt of psi is equal to h psi. And if you, so h, I said, was equal to E times psi. That's this equation. And then if you computed the time derivative, you would see that d by dt brings down a factor of minus I e divided by h bar. And indeed, that will cancel the I h bar appearing right here. And so if you just plugged that plane wave into Schrodinger's equation, you would get E psi is equal to E psi. Okay. So that this time variation of the plane wave is a property of Schrodinger's equation. Indeed, we guessed Schrodinger's equation by looking at that, by starting with the plane wave and thinking about how it should depend in time given the energy and the momentum of a free particle. Good. Okay. So we saw that plane waves have definite momentum so that the variance, delta p, defined as the square root of the difference between the expectation value of p squared and the square of the expectation value, is equal to 0. So that means that by the uncertainty principle, if they have a definite value of momentum, they should have a completely indefinite value of position. And indeed, the absolute value of psi squared for a plane wave is just equal to a constant independent of x. So that means that the variance of x, that is to say the difference between the expectation value of the square of the operator and the square of the expectation value, is infinite. So that's why this is consistent with the uncertainty principle. So, of course, for a more general state, delta x times delta p is bounded below by the uncertainty relation that their product is greater than h bar over 2. So 0 times infinity, well, that's a little bit ambiguous. Really, if I wanted to be precise, I shouldn't talk about an exact plane wave. I should talk about something a little nicer, where delta p is not 0 but small, and then delta x would be not infinite but large, and they would have the property that the product of that small times large number would be something bigger than h bar over 2. And I'm not going to prove the uncertainty relation to you in this class, but it's not a difficult thing to do. What I would, however, like to discuss is exactly what property it is of the observables x and p that lead to this uncertainty relation. But before I do so, let me pause and see if there are any questions. Yes?
To prove the uncertainty principle, will you go from the Schrodinger equation, or will you use arguments like to observe the particle and you shine light on it?
I'm going to present to you a more general version of the uncertainty principle that will give you at least a hint as to how it's proved. It turns out that it's very simple. It's just some mucking around with algebra. Okay. In fact, it's something it's something that you may prove in a linear algebra class. Okay, but you wouldn't know that you've proved it because it has a different name. There's some inequality that begins with S. Schwartz, yeah, it's a consequence of what's called the Schwartz inequality in linear algebra. It's purely mathematical. The Schwartz inequality is not usually phrased this way, but it's basically this. So before I do that, however, let me discuss one more thing. So we saw that it's possible to write down a state with a definite value of momentum, but a completely indefinite value of position. Let's ask now whether you could do the opposite thing and consider a state with a definite value of position, but a completely indefinite value of momentum. And if you think about it a little bit, that's actually not too hard. Okay. In particular, a state psi, which takes the form of a delta function that is equal to 0 if x is not equal to x naught, and infinity if x is equal to x naught, normalized so that its integral is equal to 1. That is an eigenstate of the operator x hat with eigenvalue x naught. Okay. Why is that? Well, the operator x hat acting on psi just takes it and multiplies it by the function x, so that x times the delta function. But since that delta function is 0 when x is not equal to x0, that's just x naught times the delta function. And so this state has definite position, but indefinite momentum. Just as the plane wave had definite momentum and indefinite position. Now, I've only written down the x dependence of the state here. I haven't written down the time dependence. So let's just say, let's just do it at time t equals 0 here. In order to determine the time dependence, we would have to know the Hamiltonian of the theory. And for a free particle, for example, that's something that you could solve. And for a free particle, it actually turns out that if you took our state being a state with definite position and you let it evolve in time, according to Schrodinger's equation, for a free particle, it would spread out very rapidly. That's just the statement that if a particle has completely indefinite momentum, then it could be flying every which way, and there's a sense in which it is flying every which way simultaneously, and so the wave function will spread out very rapidly. Yes?
Going back to the previous state, you have the wave equation in completely indefinite position. How do you even know that it's there at all? How do you know it's...
Well, if you observe the particle, if you measure, let's put it this way, if you have a plane wave, if I constructed 60 identical plane waves, wave functions, and I handed one to each of you and I said, find the position of the particle, then you would each perform a measurement to determine the position of the particle and you would obtain an answer. Okay. You might obtain 0 or 1 or -1 or whatever. But it'll have the property that the probability distribution would be completely flat and evenly distributed, with x being between -infinity and infinity. Okay. So the question then that I want to ask is, what property is it of position and momentum which makes it impossible to have a state with definite values of those simultaneously? Okay. Why is it that, what's special about position and momentum that makes that true? Okay. So in order to answer that question for you, I would like to present a generalized version of the Heisenberg uncertainty principle. So last time I presented to you the Heisenberg uncertainty principle relating the variance in x to the variance in p. But in general, given two observables, that is to say, two operators, A and B, then the product, then in any state, psi, the product in the variance in A with the variance in B is greater than or equal to the absolute value of the commutator between A and B, or I guess I should say the expectation value of the commutator, where the commutator between two operators is defined to be the product of AB minus BA. So if A and B were just numbers, numbers have the property that one number times a second number is the same as the second number times the first number. Okay. We all learned that when we were young. But operators do not have that property. For example, if you just think about matrices, n by n matrices, matrix 1 times matrix 2 is not necessarily the same as matrix 2 times matrix 1. for certain choices of matrix, it could be the same. But for other choices of matrix, it might not be the same. And it turns out that it is this commutator, the difference between their products, that is a measure of the extent to which we cannot have states with definite values of those two observables simultaneously. Okay. Just to say that again, the extent to which A and B cannot have definite values simultaneously is measured by their commutator. Okay. And I suppose I need hats on everything. So let me give you an example. We saw that the position operator, or sorry, the momentum operator, is minus IH bar times d by dx, and the position operator multiplies you by the function x. So let's compute the commutator. Okay. That is to say, let's compute the product of the operators x times p minus p times x. Or, to think about that a little bit more explicitly, that's minus IH bar times the operator which takes a function and multiplies it by x times the operator that takes the derivative with respect to x minus derivative with respect to x times the operator that multiplies a function by x. So in order to think about this a little more clearly, it might help you if you imagined that there was a wave function sitting over here, okay, and that all of this derivative was just taking the derivative of everything to the right of the derivative. Okay. So then you could just apply the product rule to the derivative here. So the derivative of x times psi is equal to x times the derivative of psi plus psi times the derivative of x. And what's the derivative of x? It's equal to 1. So you see then, just forgetting about the wave function that we were sitting here, that this is equal to I times h bar. Since, just to write it out a little bit more explicitly, x times d by dx of psi minus d by dx of x times psi is equal to minus psi. So we can see then the reason why it's impossible to simultaneously measure position and momentum is that the position and momentum operators do not commute with one another. Okay. So position and momentum operators do not commute. So so I'm not sure if that's a word that you've seen before. So we say that two operators commute. So A and B commute if AB is equal to BA, or in other words, their commutator is equal to 0. And it's only those observables with vanishing commutator, that is to say those observables that commute, which can really, that can have definite values simultaneously. So we saw that X and P are examples of observables that cannot have definite values simultaneously. We've also seen an example of observables that can have definite values simultaneously. So, for example, the momentum operator and the Hamiltonian of a free particle, 1 over 2m p hat squared, commute. Why is that? Well, P commutes with itself. P times P is equal to P times P. Okay, that wasn't very hard to prove. And so that P squared times P is equal to P times P squared. Okay, that's just a little harder to see. And that means that for a free particle, it's possible for the particle to have definite values of its energy and its momentum simultaneously. But it could not, for example, have definite values of its energy and position simultaneously. So, for example, if you wanted a fun exercise, you could compute the variance in the position and times the variance in the energy, or the Hamiltonian, for a plane wave. That would be a fun exercise. And you could either do it directly, or you could do it by, well, actually, that's actually a sort of hard exercise, now that I think about it. Okay. But it would be non-zero. You would have to be a little careful. Any questions? No questions? Yes.
You say that your states all belong to space.
Yes? So states live in a vector space, okay. But the operators that act on that vector space don't commute with one another. So you don't multiply two vectors together. You multiply matrices together. And the matrices act on vectors. Okay. You take a matrix, you multiply it on a vector, you get another vector. And matrices don't commute with one another. Matrix 1 times matrix 2 is not equal to matrix 2 times matrix 1. Yes?
What is the time operator?
There is, in quantum mechanics, okay, that's an important question, because in special relativity we learned that space and time should be treated on somehow the same footing. In quantum mechanics, the theory that I am describing to you is non-relativistic quantum mechanics, where space and time are treated on different footing. So there is a space operator where you measure, because it makes sense to talk about measuring the position of a particle as a function of time, but you don't measure the time of a particle. If I threw a piece of chalk at you and I said, what is the time of that piece of chalk? You wouldn't know what I was talking about. And you would be wondering why I threw chalk at you, okay? But if I threw a piece of chalk at you and said, what is the position of that chalk as a function of time, you could answer that question, but you still wouldn't know why I threw chalk at you. Okay. Yeah. Good question. So, much like the Bohr model, the uncertainty principle provides a great way of estimating quantum effects. So you, in your lives as physicists, will spend lots of time solving Schrodinger's equation for all sorts of interesting systems and understanding the implications of this. But really, in this is not a class where I want to go into the details of quantum mechanics. So in this class, really for the next lecture or so, what I want to teach you is that the uncertainty principle delta x, delta p is greater than or equal to h bar over 2 is great for performing estimations. So just an example of that. Okay. So let's imagine that we have a particle in a box of size L. Then just the statement that that particle is confined to a box tells you that there is some uncertainty in the momentum of order h bar over 2L, which tells you, because energy is p squared over m, that there is some uncertainty in the energy of order h bar squared over 4 times m L squared. So what that means is that if you put a particle in a box, it can't have zero energy. The definition of the word box means that the particle's location has been specified to an amount of size L, the size of the box. And so simply the statement that a particle is in a box means that it can't have zero energy. A particle in a box must have some minimum energy. And this uncertainty principle allows us to, at the very least, estimate that energy. And that energy must be of order h bar squared over ml squared. Okay. Indeed, I believe that on the problem set that you just turned in, you estimated the energy of a particle in a box using a version of Bohr's model, and presumably you found exactly the same answer. Am I correct in remembering that? But you were supposed to. Am I correct in remembering that? We had an n. Yeah. Okay, good. And n was an integer. Okay, so n could have been 1. So this can also be derived in the Bohr model. So the Bohr model and the uncertainty principle are the two tools that we have available to estimate the size of quantum mechanical effects. We'll discuss this more next class on Monday. And I remind you that we also have class next Tuesday because of Tuesday is a Monday. Okay, is it
Tuesday is Monday, but Wednesday is It's all good.
It's Monday, Wednesday? Not Monday, Tuesday? Okay. Because I know that it was, yeah. I thought we have 2. Wait, we have 3 days of classes next week? Okay. I'll see you on Monday.